In this video, I'll walk you through how to use Beyond Labs and how to work an actual experiment in Beyond Labs. If you haven't used Beyond Labs before, there is this link over here where it is a simply it's a guide on how to use the different techniques in Beyond Labs like FTIR, just to make you familiar with the Stockholm NMR, TLC, melting point in there. I'll try to explain today how to use the extraction, the distillation, and I'll include those videos as well as a reference because these are considered to be a purification techniques that you would need to use after every single synthesis. So try to watch these videos in there, and after you do, you can start the lab. So you can access the lab from here. What you need to do is just to click on the lab, and once you click on the lab, the lab worksheet, it's going to open together with the questions, together with the lab Stockholm. Everything is going to open for you. All what you need to do is just hit. There is a button over here, which is your assignment. Just hit on it. I'm just going to go ahead and hit on teacher preview over here. And this is how the lab looks like. You do have your procedure in there. Normally, they start with the target of the compound that you need to make. So we are making benzoic acid. Okay, and it's called alcohol oxidation. So this means that you are oxidizing an alcohol into carboxylic acid. So we already talked about this reaction in organic 1, oxidation of alcohols, primary alcohols into carboxylic acids. This means that you are using an oxidizing agent, which is a strong oxidizing agent. In there. One thing that I want to mention, if you go to eCampus, for every single lab that I post, I always post a video on the reaction and on the mechanism of the reaction. So please make sure to refresh your memory and watch that before you go ahead and attempt the lab. Okay. So here you go. So this is going to be the lab. Now, to make it easy on you, whenever you are working with the lab, try to open both the worksheet and the lab Stockholm side by side. So open them in a different window. In there. So we're going to start with the synthesis procedure. It's telling you that you're going to click here in order to open the lab. Now, if you scroll down, this is the procedure for the lab. And after the procedure in there, these are the questions that you would need to submit. Okay, you have to hit submit question every single time, or else it's not going to save your question in there. There are some question answer questions in there specifically for the mechanism, and if this is the case, you guys, all what you need to do is just write it down, take a picture of it, and attach it. Let's say if the file is too big, try to make it small whenever you want to save it. It's easier. But if you cannot make it small, then I haven't set this yet, but I will do that tonight. I will have like a folder in here or a link so that you can submit anything that is too big that you cannot submit on Beyond Labs. You come to the lab and you submit that as well. Okay. So let's go ahead and minimize this over here and open a new window. So you're going to go ahead and open the actual lab, open it in a new window tab in there, and put them side by side like this. Okay. I'm going to go ahead and have the procedure very tiny over here so that I have enough place or enough room for my lab. Okay, so the first thing that I want to do over here, let's go ahead and write the reaction. So I know that I am starting with, or I want to make benzoic acid. So this is going to be benzoic acid. Okay. So this one is benzoic acid. And to make this acid, I am doing alcohol oxidation. So I'm starting with an alcohol. Because this is an acid, I know that if I oxidize a primary alcohol, this one is a primary alcohol. It's a primary benzylic alcohol here. So if I oxidize a primary alcohol by a strong oxidizing agent, then I'm going to get the acid, the carboxylic acid. And if I use a mild oxidizing agent, then I'm going to get the aldehyde. They're not asking about the aldehyde. And again, I am not adding any carbons in there. So I do have one carbon here. It's going to be one carbon there. Okay, here you go. But if they are asking me about the aldehyde, I need to use a mild oxidizing agent. There is one mild oxidizing agent that we talked about, which is the pyridinium chlorochromate, PCC, in presence of dichloromethane. This is a weaker oxidizing agent than sodium dichromate. Okay, this is Cr2O7, sodium dichromate, or we can use a chromic acid, or we can use chromic acid in there, the H2CrO4, this chromic acid in there, anything that has chromium in it, and the hydrogen will make it a strong oxidizing agent. So I can use a chromic acid in the presence of water. All of those are considered to be a strong oxidizing agents. Okay, so this is going to be my target. I gotta start with a primary alcohol, and the primary alcohol has to be a benzyl alcohol. This is called a benzyl alcohol. So I'm going to go into the stockroom in there, and I'm going to go into the alcohol oxidation station there, and I'm going to choose my reactants. So my reactants are going to be the benzyl alcohol. Anything that I choose here, it's going to appear on the blackboard. So I'm going to choose the benzyl alcohol. The moment I choose the benzyl alcohol, it's going to immediately go into the flask in there. Now, normally, whenever you're doing any reaction, you need a solvent. And the solvent that you use depends on the reactants that you are using. I know that benzyl alcohol is not water soluble, so there is no way I'm going to use water in there. Ethanol is the same thing, because ethanol is water soluble as well. So there is no way I'm going to use those two. So definitely I'm going to use the ethanol, the diethyl ether, I mean. So just hit on the diethyl ether, and both are going to be here. So if you go ahead and bring the cursor to the flask, you're going to see both the diethyl ether, which is the solvent, and your reactant in there. Always your flask has to contain a solvent and the reactant, okay? So after you do this, we're going to go ahead and bring it all the way to the hot plate. And after we bring it to the hot plate in there, we're not going to put the condenser yet, because we want to put our reagent. We didn't put our reagent yet, so there will be no reaction. So our reagent in here is going to be, let's see, what do we have there? We do have the chromic acid. Do you see that? This is the chromic acid in presence of sulfuric acid. This is a strong oxidizing agent, and this is what I need for this reaction. So I'm just going to go ahead and bring it all the way here. And you can easily see that the color of the solution changes. I did not start the reaction yet, or actually I did, but I want to finish up the reaction in there. All I did is a color change. The reaction will not happen unless I start heating the solution up. So I'm just going to go ahead and bring the heating mannitol in there, slide it underneath. I'm going to get the condenser all the way. The condenser is a must. And then nitrogen gas is also a must in there. Why it's a must? Because if you don't have nitrogen gas, whenever you are using heat, everything is going to explode after a certain amount of time. Pressure is going to build up, everything is going to explode, and we don't want this. Okay, and then you have the time in there that you can start your reaction. To start your reaction, all what you need to do is simply hit start reaction over there, and you can advance the time by an hour by a 10-minute over here, and by a 1 minute there. Before I start my reaction, I'm just going to go ahead and run some TLC there. Here you go. And this is your TLC there. I've talked about the lab book, and the lab book is very important for saving all your spectrums, all your TLCs. And all what you need to do is just hit save. Now, what does this TLC tell me? Every time you're looking at the TLC, you are going to see spots in there. And the first spot always to the left is a reference. So this is what the reactant looks like before anything is happening. This is going to be the reference. And it's always going to be there. It's not going to change position, because whenever you are doing a TLC, you always need to have a reference to refer to. Now, whatever is in your flask is on the right. So on the right now, I still have my reactant in there, which is basically the benzyl alcohol. So this is a benzyl alcohol, which is a reference, and this is another benzyl alcohol in there that is found in my flask. So at the end of the reaction, I should not see this. This should completely go away. And this is why we say we monitor the reaction with a TLC, because the TLC will tell me exactly when the reaction is going to stop. When this spot over here, I don't see it anymore, I see it in different position, then this means that I reacted all my reactants. I have no reactants, I only have the products. So all what you need to do is just save it, and that is going to be in your workbook. I would see this, so you don't have to do anything else. You don't have to download anything. You just save it in your workbook in there. Now, while you're doing the experiment, you guys, you can go ahead and answer some questions in there, because it's asking you list all the starting material, solvent, reagents. So we can go ahead and write everything in there and submit the question. We're not done yet, so I'm just going to go ahead and advance by 10 minutes and count the time in there. So here you go. And you can easily see over here the contents of the flask and what is happening as you are advancing the time in there. Okay, here you go. So I am counting the time in there so far. It took 30 minutes, but 30 minutes, notice that what I have over here is my product. I no longer have the benzyl alcohol. I have now, the reaction is done. That's it. So as long as you don't have reactants in your flask remaining, this means that the reaction is done. So you got to stop the reaction. So here in the reaction, what do I have? I have my product, but I have stuff with it that I want to get rid of. At the end, our target is to just have the product, which is the benzoic acid. So what I'm going to do over here, that's it. I'm going to stop the reaction. To stop the reaction, all what you need to do is grab your the separatory funnel. Actually, before doing this, let's go ahead and get the TLC. Okay, so we're going to get the TLC, and the TLC tells me over here, you know what? I don't have the benzyl alcohol anymore. I have another product in there, which is the benzoic acid. Now, it's telling you over here in the questions, what is the TLC RF value in order to measure this guy? Guys, all what you need to do is bring a ruler, bring it to the screen, and from the midpoint in there, from the midpoint of that spot, you can measure it all the way to the spotting line, and you know how to get the RF value in there. Again, there is a video for the TLC. So all what you need to do for the RF. So if this is your spot, this is your simply your spotting line there, and this is the solvent front. So that is the solvent front. To get the RF is equal the distance from the center of the spot to the spotting line, which I'm going to call it X, divided by a longer distance over here from the spotting line to the solvent front, which is Y. So RF is equal to X over Y. RF is always less than or equal to 1. It can never, ever exceed 1. So whatever value you're going to get, it has to be less than or equal to 1. If it's equal to 1, then your spot is all the way to the solvent front. See what I'm saying? So pay attention to this. Means that your product is extremely nonpolar, and it migrated all the way up the column or up the plate. Okay, so I'm just going to go ahead and save that, and it's automatically going to save. See, it's automatically going to save in there. Go ahead and answer the questions for the TLC. Asking you to draw the mechanism. Just go ahead, look at the video, and draw the mechanism of the reaction in there. Now I'm going to go ahead and stop the reaction. To stop the reaction, I'm going to bring the separatory funnel all the way here. Okay, so if I bring the separatory funnel in there, what's going to happen is that my solution, which is found in the round bottom flask, is going to go immediately to the separatory funnel. And in the separatory funnel, it's telling me that I have a product mixture, and the product mixture is over here. It's telling me what is that. Now, you got to be really careful to know what type of solvent you want to add in order to get rid of the stuff that you don't need. Normally, diethyl ether, I don't care about because this one can easily evaporate. What I care about here is the chromous sulfate that I want to get rid of. So I analyze what is chromous sulfate and what solvent from these three dissolves the chromous sulfate. If I have, normally this is the rule. If I have here an acid, I would add a base in order to neutralize it because I'm creating an aqueous layer in there, so I would add a base. If I had here a base, I would add the acid, which is HCl. Chromous sulfate is neither. So chromous sulfate can easily be dissolved in water. So I'm going to go ahead and add water. Okay, let me see. I'm going to go ahead and add water in there. Now, when you add water, you're going to see that you're going to have two layers in there. And there is a note with Beyond Labs that every time you want to add a solvent, they add ether as well with it because ether can easily evaporate. You want to create those two layers, which are the aqueous and the organic layer. So it tells you that the bottom layer is the aqueous and the top layer is the organic layer. Normally, the aqueous layer is the layer that has color, and the organic layer is the layer that has no color in it. We want the organic layer because benzoic acid is in the organic layer. So I'm just going to go ahead and grab the organic layer, just the organic layer, leave the aqueous. I don't care about it over here. So that is my product. And notice at the final stage, I managed to isolate the benzoic acid. I managed to isolate the product. Just the product. I don't want any impurities with it. Now, let's say, for example, if you did the extraction and you still have impurities in here, then in this case, you would need to do an additional step, which we call distillation. And this is going to be the distillation setup. So all what you need to do is just go ahead and bring that distillation all the way into this station and bring your flask into the distillation setup there and turn on the heat and monitor the temperature of the reaction because one of the components will evaporate at a lower temperature, and whatever evaporates at a lower temperature, that needs to be your product that you would need to isolate. Okay, in there. So here you go. So I've managed now to get my my product. In the separatory funnel, it's telling me that I have the chromous sulfate, the water, and in the flask, it's telling me I have my benzoic acid. So, so after I do this, I now need to do some analysis and therefore the benzoic acid. So I'm going to bring the proton NMR. I'm going to do proton NMR analysis, and now I'm going to bring the proton NMR all the way to my flask. And when I do, here you go, all the way to my flask. And when I do, I'm going to get the NMR graph. I'm just going to go ahead and hit save. There are a couple of questions on the NMR that I would need to answer. So I'm just going to go ahead and hit save and close that. And it should show here so that I can refer to it and get back to it. And then I would need also IR. So I'm just going to go ahead and bring the KBR plates all the way to my flask. And here you go. And this is going to be the FTIR. Normally with Beyond Labs, they start analyzing the FTIR first and then the proton NMR. And this is how I want you to analyze it. There are spectroscopy tables on eCampus. Please use them because they are very important. So it tells you whenever you want to read the IR, you have to read it from the left to the right. Okay. Now I know that if you look at your product in there, so I am analyzing what? I am analyzing in the FTIR, I am analyzing the functional group. So what makes this a benzoic acid? What makes it an acid? What makes it an acid is simply the carbonyl, and it is the OH, right? This is what makes it an acid. I don't care about the benzene, although benzene is important and it's going to have a signal in the FTIR, but what makes it an acid is the carbonyl and the OH. And this is what they want. They want the functional group that makes your organic compound. Okay. So I'm going to start over here. I do have my OH signal. See, this is going to be my OH signal. This is not the sp3ch stretch. This is not a functional group. This is an alkane. So please do not include it over here. Don't include any alkanes because they are asking about functional groups, and alkanes are not functional groups. So it's telling you position 1. It's not labeled, but they told you read it from left to right. So I'm going to start with the first peak, and that is going to be position number 1. So in position number 1, I do have the answers over here. I'm just going to show you what they are looking like, what they are looking for. You can either write a number or write a range. It doesn't matter in there. So anything above a 3,000, you can go ahead and write it down because this is going to be your OH stretch, right? So for position number 1, I do have my OH stretch. The OH of what? The OH of the acid, but you don't have to write the acid. Just go ahead and write the OH stretch in there. Don't write it as alcohol or as an acid because it's not going to take it. So make sure that because they're asking you about the functional group, so go ahead and draw the actual atoms that constitute the functional groups in there. Now, the second position is the carbonyl. The second position that I care about, position 2, is this. This is the second peak. So that is the carbon double bond O. So what they are looking for, the carbon double bond O of the acid, which is approximately at 1700. And then the functional group is the C double bond O. So write down C double bond O in there. Okay. With position number 3, if you look at the acid, because I am focusing on the acid, they are focusing on the stretches of the acid. So on the stretches of the acid, I have the sp2co. This is the peak number 3 in there. Notice that there is nothing for the benzene. Nothing for the benzene. Why there is nothing for the benzene? Because I know that benzene is at 1600, but it's very, very small in there. So this is why you don't even mention the benzene, but there is a sign that you have a benzene, by the way, which is this peak over here. This peak at 700 is the carbon. It tells you that it is the carbon double bond carbon of the benzene. So you know it's a monosubstituted benzene, but it's so far away in there. See how many peaks that is? So this is why they only care about the carbonyl, and also they care about the sp2co stretch. The sp2co stretch is this one over here. It's around 1300. You can easily see that. And this is the sp2ch. Yeah, it is around the 300. And this is the CO stretch. The CO stretch, which is the sp2 carbon connected to the oxygen. This is what they want from the FTIR. I'm going to hit save over there. I'm going to close that. Now for the proton NMR. I'm going to zoom in. Okay, so here you go. I'm going to zoom there. Here you go. I do have a lot of peaks in here, and let's go ahead and look at the peaks are already numbered, but before working the proton NMR, you want to go ahead and do the integration. There is no place to put the calculation for the integration, but I just want to show you something that will make it easier for you in there whenever you are working. So I know, draw the structure of the product, which is the benzoic acid in there. And I know if I look at the structure in there, if I want to analyze how many proton NMR signals I have, okay, then these are the signals. I have every different hydrogen will show a signal in the proton NMR. So these two hydrogens are the same. I do have proton A prime. So I'm going to see a signal for these two, just one signal, but that signal is going to correspond to two hydrogens. I'm going to see another signal. Let's use another color in there for hydrogen B. And again, it's going to constitute, it's going to be hydrogen B prime. So another signal in there, but it is going to be for two hydrogens. So the intensity of the peak is going to be higher. And then the last signal that I'm going to see is this HC over here, which is going to be shorter than the others because it's going to be for just one hydrogen. So I have one hydrogen, I have a peak for the acid. If I want to look at the multiplicity, we said that for carboxylic acids, for the hydrogen of the alcohol, they are not split by any neighboring hydrogens, so they always are going to appear as a singlet. Okay, as a one peak. Singlet means one peak. For hydrogen A will be split by the neighboring hydrogen. So hydrogen A is split by hydrogen B into N plus 1, into 1 plus 1. So this is going to show as two peaks. So hydrogen A will show as a doublet. But the doublet is going to be higher intensity because the doublet is going to correspond to two hydrogens in there. For hydrogen B, it's split by both. It's split by hydrogen C and hydrogen A into 2 plus 1. N plus 1, you have two neighboring hydrogens plus 1. So hydrogen B will show as a triplet. Okay? And that triplet will also have the same intensity as the doublet. And I can see this. I can see a triplet and I can see a doublet. You can easily zoom in. You can easily zoom in there to see the peaks. I zoomed in too much. Let me zoom out. So you can easily see that 0 is the TMS. Forget about it. This is the reference. Okay. Let's go ahead and zoom over here, and these are my peaks. Okay, I can easily see that I have a doublet, I have a singlet, and I have two triplets. So what is the third triplet? The third triplet is this one over here, which is a triplet, and that triplet is lower in intensity. Notice that this one is lower in intensity compared to this one over here, because this corresponds to one hydrogen, versus the triplet on 4 corresponds to two hydrogens in there. So you gotta now have an idea what hydrogen corresponds to what signal in there. They are already labeled for you. So when you are asked here that they want the chemical shift for peak 1, the chemical shift is simply you are reading the NMR spectra for peak 1. So you go to peak number 1 over here. So this is peak 1, and let me enlarge this. So you go to peak number 1, scroll all the way down in there, and read this number, guys. It's 8 point something. So that is going to be the chemical shift in parts per million. The whole scale for the proton NMR is from 0 to 12 parts per million. Okay, and I know that the region between 7 and 8 parts per million, this is for the benzene. Now, for some reason, that singlet for the carboxylic acid, normally in normal NMR, it shows at 10 parts. Actually, it shows at 12 or 11 parts per million because it is a because it is a carboxylic acid. But because I don't know why it is showing here in the benzene region. Normally it's very odd, it doesn't show, but it is showing in the benzene region, and I can easily see that this is a singlet. It is one peak. So peak number 2 corresponds to the OH of the benzoic acid. So that is going to correspond to peak number 2 in there. Okay. Now, before doing anything, there is something which is called integration, just to make sure that whatever you have here matches whatever you have there. Because at the end, they ask you, do your spectrum match your structure? Well, to match, you would need to do the integration and do the number of hydrogens for every single peak, and then match that with your answer. Now, to do the integration, all what you need to do, see those areas in there, these are the peak areas, these are relative in there. Peak number 1 has an area of 194. These are relative numbers, okay? And peak number 2 has an area of 101.7. So I can easily see that peak number 1 has twice the number of hydrogens of peak number 2. So let me show you how to do the integration. And again, you do the integration, you don't have to submit the answer for the integration, you guys, but the integration is a must just to match the spectrum with your answer. So with the integration, you are going to add all the areas together. So I have 194.55 plus 101.7 plus 84.676 plus 179.37, and simply you're going to get an answer. Let's say you get an X, okay? So you take that X and you divide it by the number of hydrogens. So you divide that by the number of hydrogens. I already know how many hydrogens I have in my structure because I can easily count them. I did the product, I can count the hydrogens in there. So count the hydrogens, and the hydrogens are 1, 2, 3, 4, 5, and 6. So here in this case, you're going to go ahead and divide it by 6. And let's say you get an M. Now you're going to take every peak area in here and divide it by M. And then you're going to get the value of integration for every single peak. How many hydrogens that correspond for every single peak. And you should match it with your spectrum in there. Okay, so you can easily know which is which. Now, because HA is the closest to this HA over here is the closest to the oxygen, to the carbonyl. So I'm expecting that this HA in here, which is proton A, to be the most de-shielded. And the most de-shielded, this means that it is pushed further downfield. So I am expecting HA over here to be the last one. So this one is the doublet. Do you see? This one is the doublet, and the doublet is all the way downfield in there. And then I am expecting the hydrogen of the acid to be over here. So these two are they are pushed further downfield because they are de-shielded. And then the hydrogens, the other hydrogens on the benzene, which is the meta and the para. For HB in there, if you look at HB is going to correspond. You have HB and you have HC. For HC in there, it is one hydrogen. So you can easily see that this has a peak area which is the lowest in there. So that is going to correspond to the one hydrogen there. And then the most shielded is the one which is all the way upfield. It's the 4 in there, which corresponds to this hydrogen over here, which is HB. And this one is a triplet as well. So the data in here matches our spectrum in there, and this is what you need to look for. So when you are filling the peaks, it tells you peak number 1. It means peak number 1. What is that? So you read the chemical shift for it. You put it in here, and then it tells you the multiplicity. This means the splitting. Check it out. If you cannot read it, zoom it, okay? I zoomed too much. So zoom it over here, and I can see it's a doublet. So go ahead and put a doublet in there, and so forth. Specify the number of hydrogens. We already calculated the number of hydrogens for this one, and this one corresponds to 2 hydrogens. You have to whenever you are looking at the number of hydrogens, you have to count all the hydrogens that correspond to the signal, and it is 2 hydrogens corresponding to the signal. So you go ahead and put it in here, and then you can easily continue the lab. Now, if you managed at the end to have your product matching the IR in the FTIR spectrum that you got in there, then simply what you need to say over here that my product matches the spectroscopy data, and then submit the question. And pretty much this is going to be your lab. If you still have further questions whenever you are working your lab, please let me know. But every single lab that we work out, we explain the reaction for. So you would need to look at the reaction. You would need to understand the reaction, understand the mechanism before you go ahead and proceed and make a synthesis method in order to synthesize that product.